Hello, calculus fans. Let's find the volume of the solid that lies below the paraboloid z equals x squared plus y squared and above the region D in the xy plane. That region is bounded by the line y equals 2x and the parabola y equals x squared. Now, we'll show you the picture here in a moment. You can see that it's both a type 1 and a type 2 region. Here's the picture expressed as a type 1 region. Notice that the upper and lower bounding curves are being expressed as functions of x. That makes it a type 1 region. The x values will go between 0 and 2. We get those values by setting 2x equal to x squared and solving for x. That gives us intersection points, which helps us create the bounds. So if we're thinking of D as a type 1 region, then we'll express it like this. D is the set of all points where x is between 0 and 2, and the y values go between the lower bounding curve of y equals x squared and the upper bounding curve of y equals 2x. Notice that the picture is important to help us figure out which one really is the lower and which one is the upper bounding curve. Let's write down a double integral for the volume of the solid. It's the double integral over D of x squared plus y squared dA. Let's now write this as an iterated integral, thinking of D as a type 1 region. Alright, so it's the integral from 0 to 2, those are the x limits, of the integral from x squared to 2x, and we'll evaluate the integral of x squared plus y squared. This is a dy dx integral. Because it's a type 1 region, we want to finish with a dx integral. We evaluate the inside integral with respect to y, and we're plugging in the lower and upper limits of y equals x squared and y equals 2x. So we'll plug those y values in, and we'll get this integral here. A bit messy looking, but actually pretty straightforward, because it's just a polynomial function now. If we clean it up, we'll get this integral, and now it's smooth sailing to the end. Compute an antiderivative, plug in the lower and upper limits, and if you simplify it all, you'll get 216 over 35. Let's now express the region as a type 2 region. What we'll do is we'll show you the region expressed as a type 2 region, but you should set up and evaluate the integral yourself. Now, it's important that you get the same answer. That's why I went to all the trouble to simplify that last answer. I want you to actually evaluate this integral as a type 2 region. Bring your work to class. Let's take a look at it. Here's the same picture, same region, but now it's expressed as a type 2 region. Notice the difference, that the curves are now expressed as functions of y. And now we're going to integrate on the inside in the x direction first, and then with respect to y. Alright, so you've got some work to do to work out this integral, thinking of the region as a type 2 region. Okay, that's all for now.